All right, let's start. Hello, everyone. This is Dr. Yuzo. This is ECE 341 Power System class. And can you guys hear me?
Yep.
All right, thank you. And here I'm sharing the dog cam and showing you the two formulas we need to calculate the optimal dispatch. Okay. First of all, anyone remember what this is called? What this lambda. Anyone remember what the lambda is? Anyone remember what the lambda is? No, lambda is not Lagrange multiplier yet, right? Now, the multiplier is this. The CT plus lambda. Remember? This is the optimal lambda involved Lagrange multiplier. Here, of course, it's telling you what lambda is. Telling you what lambda is. Lambda is introduced unknown. Introduce unknown. And Kevin is saying is coordination equation. Now, coordination equation is, well, is not lambda, right? And who knows who is the coordination equation? PI, good, very good. Here is the coordination equation to guarantee the optimal total cost. Right? To guarantee the optimal total cost coordination equation. And of course, here this pi is the same pi. Okay? This pi. This is pi. P sub I. Pi is referred to this pi. So after the coordination equations, you end up with multiple pi's, right? And then the sum of them should be equal to what? PD. And remember, the constraint is PD. Okay? Constraint is PD equals to the summation of pi. Remember this. And also, don't forget this: the total cost, minimum cost, eventually equals to what? Summation of what? CI. Right? Summation of individual generator cost function, cost value, and further equals to C1 plus C2 plus CI plus Cn sub G, right? And each one of them equals to what? Each one of them equals to a what? Cost model function, right? This is the C1 plus similarly C2. Right? Here is trying to help you recall what we have learned. And here you need to be careful some details as well. So alpha, beta, gamma, they are respectively the constant term, coefficient of first order P, and coefficient of second order P. So which is which, you need to be very, very clear, because you're gonna apply them to the formula. If you identify them wrong, then of course you end up with the wrong answer. Right? So these are the things for optimal dispatch. Not difficult, but there's some small details you need to be careful. Any questions you have? All right, if these are fine, then go ahead. Let's do more examples. I don't think we need to talk too much. Just example 2, obviously, giving you the individual generator cost function. Yeah, 3 generators, of course, this time. C1 equals to 350 plus 7.2. P1 plus 0.004 P1 squared 500 plus 3 P2 0025 P2 squared. In dollar per hour as unit. Always remember the unit. It matters. The cost is not dollar. It's dollar per hour. Yeah, dollar per hour. And here also PI in megawatt. And here the total customer power is requested as 450 megawatt. And then find what? Find a total cost difference between optimal dispatch and evenly share the power among 3 generators. Here is asking for 2 different cases. One case is really optimal voltage. Second is evenly share the power, right? Evenly share 450 megawatt among those 3 generators. In that way, of course, you're going to come up with a cost as well, right? So what's the difference between these 2 costs? Here is that 0.005. Kevin is asking for here, and yes, this is 0.005 0025 times P2 P sub 2 squared. I think I need to talk too much. I give you guys 8 minutes up to 4:20. I will present the solution. And if any questions, you just bring it up immediately. Okay. All right, go ahead. So the basic idea should be you're looking for the optimal, or say the minimum total cost, right? And then you're looking for the total cost for the second case, which is evenly shared. Right? And then you do a subtraction between two costs to find out the answer. Right? That is so-called total cost difference. Right? Well, here Sawyer got the answer of this is the difference, right? This is the difference between two price, right? Two cost, right? $20. It's close, but maybe there's some roundings because it's hard to be 100% same as mine. Okay, but around $20 is both part is right. I mean, if you end up with 200, then definitely wrong. 20.75 is close to what I have. So first of all, what is the lambda value? You guys are looking for lambda first, right? You need to understand. You need to find lambda first. This is what I did. What we did back in the example 1, right? The lambda equals what?
I got 8.
Good. Okay. What is the unit?
Dollars per megawatt hour.
Dollar per megawatt hour. Good. Good. That's right. Okay. Good. Good. Several of you guys got the right lambda. The next is the P1 through P3, right? Okay. You got them right. So as I said, the lambda first of all equals to 50. Right, this is the answer for lambda. Based on which we got P2. I mean P1 through P3. Okay. P1 through P3. And they're respectively equals to 100, 140, and 210. And obviously you sum them up equals to what? Exactly 450. Exactly 450. It makes perfect sense. P1 through P3. Then next is go to case 1, which is optimal dispatch. Optimal dispatch equals to what? Equals to C1 plus C2 plus C3 then. This requires some patience here, all right? You need to substitute p-values into all three. So what do you got? 350 plus 7.2 times p1, which is 100, plus 0.004 times 100 squared, right? Plus, similarly, do the rest of 2. And yep, I got exactly same value as Noah did. The difference is $21 at $21. $21. So optimal dispatch, what is the total price? The total cost, not price. The price is higher than this, right? Remember our discussion? Or price won't be same as their cost. Otherwise, they have no salary to their employees. I'm sorry, this is the dollar per what? Hour. The cost, there's no megawatt there. Just $1 per hour. Next thing is evenly share. What does it mean? Evenly share means P1 equals to P2 equals P3, right? This is what I mean by evenly share. Total is 40, evenly shared by 3. Each got 150 then. Then you do the total cost this time equals to, I'm using a prime here to differentiate from the original C1 through C3. Okay? And then what do you need to do? Substitute those powers into 3 different cost functions. Right, one more time. But here, there's a tip, right? Obviously, there's a tip, which is what? This value need to be what? Compared to this guy. Who is higher?
Bigger.
Absolute bigger. Right? Good, very good. Okay. Some of you guys realize this. This money, this cost must be bigger, than, otherwise no sense. In other words, this couldn't be the optimal dispatch. It makes no sense when you're working for like what, 2 or 3 lectures, and eventually evenly share, gonna save some cost. Wow. I'm gonna be egged. Right. So, but anyways, and if everything calculated correct, and then you're gonna end up with what? You're gonna end up with well, not too bad actually, better than I thought. Better than I thought. Better than I thought. Then what is the difference? As the final answer, the difference in between is just subtraction between this and this, which is $21. 21.5. Can say this. Is $21 big or small? Like I said, less than I thought, right? However, in terms of value, yes, it's not that big, $20. However, is it big or small? Well, it's a ridiculous question, but you know what I mean, right? Is this $21 big or small? It's not small. Okay. Why is not small? This is lots of hours. Okay. And this is $21 per hour. Every single hour, there's $21 difference. How many hours? You count how many hours you are using power, right? How many hours you're using power. And so basically one lecture, how much money we are saving, right? One lecture we are saving about $30, right? So it's a difference. It's different. Assuming we are using this amount of power, of course. So take a look to see any questions. Any questions you have? All right, if this is fine, then I think this is easy enough. This is enough. I want to talk about this. Okay? I want to talk about this. Okay, the next thing. Yeah. I actually can't remember what exactly is the bulletin number. Check my notes here. Okay. Number 5. The optimal dispatch, so far we have been talking about is what? The optimal dispatch, neglecting the loss and the generator limits. Number 4 here. This is the title. This is the title we had. Okay. This is the scenario we have been studying. We are neglecting the loss and the generator limits. So I want to talk a little bit about how to involve them. Anyone has any idea how to mathematically involve them? This idea is not something new. You just trying to link what we have learned. How to involve that. In other words, how to economic dispatch of generation if we including power loss and generator limit. Anyone has any idea how we involve them? The rough idea. We don't need to be very specific. How to involving them. Previously, we didn't. Right? We didn't. Now how we involve them.
Would it be part of the cost function as a negative?
Close, but no. The cost function is cost function itself. We're trying to keep it. Any other idea?
Do we need to change the coordination equation?
Coordination equation. Not there yet. Upper level of idea. Mathematically. Keep thinking. This is very helpful. How we involve them. Any idea? Keep thinking. Anyone? Neil's saying adding power loss to PI, the coordination equation. No, we can't directly do that. We can't directly do that. It's not optimal. And that won't be optimal. How to find the optimal? You need to go back to the original idea. How we find our optimal? Develop Lagrange multiplier, which is what? Equals to what? Objective function. Do what? Lambda I times what? Equality. What constraint? Actually, we have a summation here because we might have multiple equality constraints. And then do what? Plus summation of another introduced new unknown UI times what? Inequality, right? Constraints. This is the original idea. So if this makes sense, then let me ask you guys again. He involved the power loss and the generator limits into 4, where we didn't.
We could put the generator limits in as an inequality constraint.
And
the power loss we could subtract from or add to our PD in the
very good, very good, great.
I was getting there.
The PD, yeah, that's the right track. Yeah, that's the right track. I'm pretty sure he understands. But basically, just because PD is what our equality constraints previously, right? So translate Noah's idea is basically your power loss into here, generate limits into here. Yeah, perfect answer. Does everything make sense? This idea. This is how you apply the math. Okay? We learned a lot of math, and I still remember Anil asked that question. He asked basically, what we are learning this for? Right? Translate his question into this language is basically what we are learning the math for. This is the optimal dispatch module, why we are learning this math. And here, again and again, prove we should learn the math first, okay? Because everything is trying to applying that math, The idea is just nothing but applying that math. So specifically, the next step is basically still identify each one of them, right? Just identify these 3 things, basically. Or so this is a single individual one. This is a group. This is another group, right? So objective function, fairly easy, right? Objective function. But remains as our cost function. Remains as this. And each individual generator cost function is a function of the power assigned. This is easy. Next, equality constraint. Previously, what we had is PD equals to summation of the total power, right? The total power. This is the customer request, this amount of power. And then now your generator generating, how many, the summation of them must be equal to, no less. You generate more, you're paying for the customer. That's not good for a company. If you're generating less, then the customer is going to be pissed off. So no more, no less. Exactly equal. That's why it's equality constraint. Equality constraint. Now what? How do you involve the power loss? This power loss is basically a constant. Assume the easiest case, constant. What do you do? Not PD, right? But what? PD plus loss equals to. Does it make sense? This was the previous case. Now we are involving the loss. Loss means what? Not only fulfill the requested power from the customer, but also you need to count in the loss. Together, the sum of these two belong to the responsibility of the consumer entity. That makes sense. So you generated power need to fulfill the sum of both, or sum of both. This is an equality constraint involving the power loss. Next is inequality constraint. Trying to involving the generator limits. What does it mean by generator limits? It's actually not very difficult. It's just each generator has a power limit. Makes sense. This is the individual generator power, generated power. This limited into a range. So this is the limit of the generator, which is inequality constraint. But of course, this guy, you need to be careful. Oh, where's my black color? Oh, here. Yeah. How many equality constraints here? Or so how many groups? These are two, right? Does that make sense? Equivalent to what? Pi greater or equal than Pi minute. Pi less or equal to Pi maximum. Does it make sense? This one. You need to realize this is actually not only one inequality constraint, two. Yep, Kevin got it. All right, two. It matters because you're setting up, you're assuming different groups of what? Unknown, remember? Unknown U here. Not U1 through U, say, NG. This time you need to assume what? U1 minute through U1 minute, UNG minute. For the second one, you need to assume U1 maximum to UNG maximum. Does it make sense what I'm talking about? Okay, let's do it then. Total function. CT as objective function goes first, and then plus the lambda. And lambda times the equality constraint, right? Equality constraint. You notice that we only just need to assume only one unknown, lambda, same as the previous case, right? And to involve everything. Parenthesis is what? PD plus PL minus summation of PIs. Okay? Done. Or involving the equality constraint. Second, to the generator limits here, power limits here is a little bit tricky. We call these as what? Two groups. This group is meaning what? How many? P1 is greater than P1. Doesn't make sense. P2 equal or greater than P2 minute. All the way to PNG greater or equal than PNG minute. Can you see why I call it group? How about the second group? P1 less or equal than P1 maximum. P2 equal or less than P2 maximum. All the way to PNG less or equal to PNG maximum. And you'll see two groups. It's not like equality constraint here. Just only one equation here. This is literally just one equation. Here is a sum. That's why you have I here. But it's basically it just means the one single equation here. Okay, so this eventually turned out to be not a group, just single one equation. So P1 plus P2 plus PI plus not up to P and G. Therefore, go to the further to the Lagrange multiplier. This is a little bit complicated then to deal with these two groups of inequality constraints, right? So what do we need? Let me start from second line. So first of all, you introduce first U1 minimum times what? Times P1 minus P1 minimum. Plus U2 times P2 minus P2 minimum. Plus all the way up to U and G. Of course, U2 here is a minimum. And G minimum times P and G minus P and G minimum. And then plus what? The second group, U1 maximum. Because you need to differentiate this U1 and this U1. They are not same U1, right? And here, the P1 minus P1 maximum. Plus all the way to U and G maximum times P and G minus P and G maximum. Finally, done. So this is how you build up the Lagrange function for including the power loss and the generator limits. Any questions? Does it make sense, everything? And from here, what we should do next step, we should do from here. Anyone knows what's the next step? Simplify. Well. Yeah, basically you're complaining is too complicated, but this is what it is. It's you can simplify. You can do a little bit simplified though, but not actually. You can do this, right? You can do, for example, these part, these U1 through UNG minimum. this part is actually equivalent to what? Since they are summation, so you can do a summation, right? UI minimum times PI minus PI minimum. Does that make sense? You can do a simplify like this, but this is not actually simplified, just a rewrite. Okay. And for same, the second here down here can be written as summation UI maximum times parentheses PI minus PI maximum. This is so-called simplified. That's all you can do. I mean, rewriting them. And then what's the next step? So you're saying derive the equations for lambda and the u use. Yeah, that's right. And how to do that? In other words, what's the mathematical behavior we should conduct? Partial differentiation. Good. Partial derivative. So based on here, we're gonna write. We're gonna write this. Okay, so partial derivative L with respect to what? PIs. Those are partial derivative L with respect to lambda 0. Partial derivative with respect to UI minimum 0. UI maximum 0. Of course, to all of them, I equals to 1 through n sub g. This is what we do. So basically, this is a generalized generic idea how to do the optimal minimum value mathematic problem. Any questions regarding this idea? Any questions? If this is fine, then we can move on. Let me talk about the quiz. Yeah, the quiz. The quiz, there is something obviously related to our upcoming exam, so I want to talk about it. The problem is not very difficult. Okay, so I guess you guys have no big trouble at all. But I want to emphasize one thing. Here, some of the power already given, right? Some of the power already given. So what we want to do are two things, right? Two things. One thing is identify those given power. Identify those given power. What I'm saying is, for example, first given power, what? S1, right? For first given power is actually S1. Right? It's given. And what else is given? S21 line flow is given. And of course, this line flow is equals what? Positive 8.5 Negative 35.5 J. Mega VA. Be careful the unit. It is here, right? It is here. At the end of the V2, so it's S21, not S12, right? Even. Point is, you're not wasting your time on finding something already given, okay? No credit, because by grading, you can tell some of the power line flow you calculated has no credit. I'm not giving you a check there, because no credit there. They're given. Okay, what else is given? That's 3.1, right? 3.1 is given. What is it? Negative 44, negative 27J, mega VA. Be very careful who is the real power, who is the reactive power. Okay, this is very important. By labeling here, you can tell that the line with arrow and the bar here, this is the reactive power. Follow this side of the line. Line is the reactive power. 44 is the active power. So 27 is reactive. S31 is also given, and also S34 is given too, right? Negative 1, negative 9J, mega VA. Given. What else? S42 is also given, right? S42 is what? Negative 60 plus 64 J map VA is S42, and S41 is given, which is negative 46 plus 17 J mega VA. Once again, these are all given. Not only no credit, more importantly, they're wasting your time if you're doing calculation on them. Does that make sense? What you need to do is just identify them by reading the graph. And what else? Miss one. S34L. The line loss between bus 3 and the 4 is given 2. Right? Does it make sense? Now, the next, try to find the rest of things which are not given. Here, there's another tip you want to follow to save time, right? For example, how about S43? S43 equals what? How to know that? You're not, well, of course you can do V4 times I43 conjugate. Of course you can, but you don't have to. This is costing more time. This is costing more time. Instead, what can you do? Line loss between bus 3 and the 4 are given 0.5, and S34 is given 2. What does it mean? How do you read this graph? So here, bus 4 is providing some active power. After losing 0.5, only 1 mega VA. 1 megawatt is received by bus 3. How many you are given? You are giving them from bus 4. It sounds like elementary school math, right? And you want to utilize that then. And what is it? It's definitely an arrow towards left with 1.5 as the value. Does it make sense? Same thing happened on the reactive power here. Yes, a certain reactive power is provided by bus 4. After losing 0.5, only 9 is received by bus 3. Right? So obviously your 3.4 just equals to positive what 1.5 plus 9.5 J mega VA. And what else you can easily know as well? How about S13? How can you easily know S13? Anyone? Oh, I'm sorry, it's not S13. The one you can easily know, another one you can easily know is what? S3. How about S3? Can you tell what is S3 and why? You don't need to go very complicated calculation, right? S3 equals to S34 plus S31. By reading the graph carefully, once again, 44 is active, 1 is active. You're summing up these two numbers. Similarly, you're summing up 9 and 27, right? So, and it was 45 as real power and 36 as reactive power, right? Anything else we can easily know without going through voltage times current conjugate? Probably not. But if from here, if you just do S12, V1 times I12 conjugate equals to V1 times V1 minus V2 divided by Z12 conjugate. Okay, don't forget the conjugate. Okay, I thought someone forget the conjugate. Well, they're gonna lose quite a bit. And after you plug in the number, you end up with the negative 5.25 plus 42J mega VA. Of course, you're ending up with the per unit value first, and you times the base value, receive the SI value. But after you having S1, 2, and then you can tell it's right here, right? This power is right here. You can, of course, immediately come up with the loss. Middle. That's good. I'm sorry, what does it mean by going out of a bus? I don't understand. What are you talking about? No, typing doesn't speak it out.
You have it as S3 is supplying power, but it's actually receiving power. So shouldn't the numbers be negative?
Oh yeah, here. But the reason I'm writing in this way is actually, if you sum these two, of course, negative and the negative. But actually, I'm seeing from magnitude wise. But anyways, yeah, following these sign is negative. Because my way to judge the power is actually by reading completely. What I mean is, you see the power on the right-hand side of the bus 3 is towards left. So the other side of the power, which is S3, is definitely towards left as well. So this is how I judge the direction of the power labeling. That's why sometimes in my calculation I'm using the magnitude, but yep, as you guys said, we should involve the sign here. S34 and S31, they have negative sign here. So should the result. Okay, so should the result. And this is S12, and after S12, you probably want to do S13 or S14. I'm doing S14 because after S14, I directly can have the loss in the middle here. Okay. S14 turned out to be 52.5 minus 10.5 J mega VA. And after S14, how to find S13? Obviously, we don't want to use the B1 times I13 conjugate. We don't have to go this way, even though this way works. But what you want to do is what? S1 is given, right? S1 is given, and then S12 is given. S12 and S14 are calculated. S1 equals to the summation of these three. That way you can find S13. That way you can find S13. 47.25 plus 36.75 J MA. Here, John is asking, why is it that we are always told negative power means delivering, but for the power at node, negative power means absorbing? How to understand that? This is because there's a sign, there's a negative convention, sign convention issue here. If you have a component here, if you're defining polarity in this way, you're defining the current times this voltage, the power equals to this times voltage. And from here, you are saying positive or negative. Positive is what? Consuming, or say absorbing. Negative here means delivering, right? You have that's because you're assigning the polarity and direction of the current here. But here, absorbing in the graph here, you're saying absorbing or delivering, you're seeing the direction of the power. It's different. You have different reference. Does it make some sense? Sort of. Well, not exactly then. Here you are saying this guy is absorbing power because you are defining towards left as the positive power. I'm sorry, because you're defining the right towards right is the positive direction of the power. Therefore, the power is negative, and you're saying is absorbing. Absorbing by what? By this end, the left end. Okay, you have different reference. There are two different concepts. It's all up to what reference you have. Okay. Yes, the power flows is because this is saying towards this direction is the power positive. And then you are following this direction current, you're following this polarity voltage. This is because here this is a node representing this node. This node representing this node, right? So this is positive, this is negative. That's why you're using V1 minus V2. Yes, it's following the sign convention, negative sign convention. Right? And following the same thing, then you basically saying here is positive, here is negative. And if you have power like this, I mean, then it means what? Negative power and delivering towards this direction. You're absorbing, you're still using this reference then. That's because you're saying absorbing because you're using this reference. I'm using this reference. Okay, if you use this reference, then it fits the negative sign convention then. Does it make some sense? Everybody? Is it too bad or? I mean, I think it won't bother you to understand the power diagram here, right? But if you try to fit the previous principle, then yes, it's different reference. Remember this, it's different reference. All right, so another thing is labeling. I think to this problem, another thing is labeling. Labeling, you need to be careful. First of all, the loss, only labeling the magnitude. There's no J, okay? You're not labeling J here. And how to differentiate the active and reactive loss then? It's all up to which side is they, right? Above the line, if this line flow is labeled as the active power, this guy here is reactive power. So is here, right? Active, reactive. It's all up to which end of the line, determining which is active, which is reactive. Okay, so you don't have to, you don't label the J there. All right. Another thing, I think just be careful which side is which. I see quite a bit of mistake on this guy, particularly. Student used 27 plus 1 and 44 plus 9. Well, no. You need to tell which is active, which is reactive. How would we denote if the line is negative J? What does this mean? The line is negative J. What does mean line is negative J? Like a capacitive line instead of inductive line. Are you two talking about the same thing or never mind? Okay. Like capacitive line instead of inductive line. So what? The line has different impedance or admittance. Well, it doesn't matter. Oh, you mean you have a positive negative sign issue? You need to clarify that. Is that what you are asking? The loss going to be negative. That's what you say. To be honest, I never seen that happen before. The loss here is the loss is positive. I never seen any negative loss here. Reactive power wise, well, never seen that either. Active power wise is definitely positive. Right? Otherwise, you're making some mistake. It couldn't be negative. We wish, however, it wouldn't be. But reactive power wise, well, I never seen negative either, actually. But it's not something impossible. Capacitive line, well, maybe. But in case loss is negative in terms of reactive power, yes, you label negative then. We have a line had a substation with capacity bank. Well, capacity bank is not considered as part of the line. The line here is considered as with just certain impedance, and capacitor bank, I think that's another bus, right? Another bus. Capacitor bank is considered as load. Yep, another bus containing a load, which is capacitor bank, trying to compensate the inductive of the line, of the load, of another load, because generally speaking, the load isn't inductive. You use capacitor bank to compensate that load. Right. Any other questions regarding this this quiz? Any questions? All right, I think the last thing I want to announce is the request from some of you guys that present you the pre-draw network so that you can easily print it out and have it ready during the exam. This request has been decided to reject it, and, but I did something. I changed the problem and the network graph to be easy enough to be repeated, which means I'm not expecting you're gonna spend a lot of time on it, on the repeating the graph. Oh, by the way, bring your ruler. Okay, so plot the graph nicely. It won't take you, shouldn't take you more than 2 minutes. 1 minute should be enough. Very easy network. Planning. I changed the problem a little bit, making it easy enough. Is that clear now? All right. Thank you, Gavin. Any other questions or requests for the upcoming midterm 2? Since we still have a kind of 10 minutes each. Speaking, come on, speaking. 8 minutes. Speaking. 100% for everyone. Well, that request is definitely gonna be rejected as well today. I don't need to think even twice. Reject it straightly. And I need to asking problem 1 little explanation. Problem 1 was what? Problem 1 gonna be. Hold on, let me get my. First of all, problem 1 is mathematical problem, and remember to follow the example as exercise. What did you do in the example? That's gonna determine what procedure you should follow in the exam problem. The nonlinear equation is given, and specifying one particular method you need to apply. Once again, remember to apply that required method rather than the other one, since we learned it too, right? And by presenting the detailed iteration steps, it means you need to have, for example, if you're looking for x of 1, you need to x of 0 plus delta x of 0, and equals to the value plus this value, and equals to what value? And then so on, x of 2 eventually equals to what value? X of 3. If you end up with x of 4 to reach the answer. Okay, then you need to present x1 equals what, x2 equals what, x3 equals what, and x4 equals what. This is the a little bit more explanation. Is that enough, Anu? Or anything else? All right. And here I'm receiving, John said, assume optimal dispatch question problem 4 will not have inequalities. Yes, I'm not planning to involve.
I think we lost audio.
Where we at? Can you guys hear me now?
Yeah, I can hear you now. You said you weren't planning to involve it, and then it cut out.
Perfect timing, right? All right, I'm not planning to involve this problem. Okay, it's that problem. Except all of you requested, okay, which I doubt. Right? So, no, I'm not planning to do this. Okay, I'm not planning to do this. Any other questions? The exam two in the past always much better than the exam 1 in this course, in this particular course. Hopefully it's the case as well, because if you didn't do well in midterm 1, then midterm 2 is your best chance to improve it, or to come back to the right track, right? And so if you're not able to come back this time, well, exam 3 is quite uncertain, and therefore, who knows if you can pass or not. Okay, so you want to really make efforts on this exam 2. Okay. Any other questions you have? Any other questions you have? Anything? Well, good. All right. Once again, I have a real-time proctoring, and not procting. It's not procting anyone, actually. It's just real-time Q&A conference open. If you want to join that before starting the exam, obviously. Okay. And leave your speaker on so that you can speak. And if you have a pad, you want to leave it somewhere else so you can focus more. So, anything else? One more time. Alrighty. So good luck with the midterm 2, and also have a good weekend, you guys. Thank you. Bye-bye.